Welcome, everybody. We've been doing implication, and now I want to try to get back to the goals of trying to think computationally about what we're doing. We know that there's in programming languages all sorts of if-thens, but that's not the kind of computation I'm worried about right now. I'm worried about a harder one, modeling the problems that we're actually trying to solve. So what I'm going to try to do now is talk about implication when resources are part of what we have to manage. So let's see what we have going on here. Suppose that we just take the standard definitions we just went through in our last lecture. We have a language for implication. I'll use the arrow with two shafts on it in between the hypothesis and the conclusion. But if you like, you can think of if-then, perfectly reasonable alternative. The introduction rule went through a little bit of steps, but we found that once you have both context and a premise that entail a conclusion, then you can turn that into an implication. The implication is nothing more than packaging that observation into symbols. So we move from the top premise, gamma with P entailing Q, into the bottom premise, gamma entails P implies Q. Implies now is the symbol for the operation of combining P with Q. We don't know if it's true or false unless we produce the evidence that it's true. Once we have evidence that it's true, such as in this stage of our program, we can then take any evidence for the premise P, and then we'll conclude Q. That's classically known as modus ponens. What else could we want to know? This seems like implication pretty straightforwardly. But there's more that we have to say, because we'll see an example now where resources throw everything we've just said into a bit of confusion. So let's think about an example where we have resources involved. If you have an egg, you can make cookies. If you have an egg, you can make brownies. Notice both of these are if-then statements, but we're not focusing on those being conditional. Right now we're saying egg entails cookies and egg entails brownies. What's the conclusion then if we're to just follow standard implication rules? I claim that this says with an egg you can make cookies and brownies. Now there's a curious understanding of this. In one sense, this is logically true. An egg can make cookies and an egg can make brownies, therefore an egg can make cookies and brownies. But another way to read this sentence would be that one egg is enough to make both cookies and brownies together. And we see there's a clear difference. We may not have enough in the recipe to make cookies and brownies simultaneously. We're resource guarding the egg. It's needing one egg for both recipes, so we'd actually need two eggs. When it comes to resources, logic can be perilous, and so we need to introduce some better explanations of what we mean implications to mean. And there's a way to do this. So let's go through what we would do in the standard logic that we've seen so far. Let me recall for you that we talked about conjunctions making an and by taking that the context gamma produces evidence for P and Q. It entails them. Once I know that P follows from gamma and Q follows from gamma, then I get to produce a new symbol, the wedge, and say gamma entails P and Q. Again, there's really no meaning with that little hat symbol. It's just notation that says I'm abbreviating what's above. In this case, it looks about the same amount of symbols, but as we get more complicated stories, abbreviating the and is a very good operation. So remember, the operations are taking the premise above to something on the other side. We're packaging facts we know in simpler packages. The next thing to recall is the way that we produce implications. This is the introduction rule for the arrow. So here we need that the premise and the context lead to Q. Once we know that, we can say that the context entails the proposition P implies Q. We don't know if P is true or not, therefore we don't know Q, but we're prepared if anyone ever gave us evidence for P, we would definitely get Q from that. That's what this implication is allowing us to say. When we put this together, we see that there is a little bit of sequent calculus that we need to do. Remember, sequents are separating premises from conclusions. So if we stack several premises together and several conclusions, then we need to read them in the order of like a tree. We follow the path to the bottom. So here we have two premises at the top. We have that the context together with an egg give us a cookie, and the context together with an egg give us a brownie. So if we use our first wedge introduction, we could say that the premise together with an egg yields B and C, both brownies and cookies. That's the beginning, but this is still not an implication. To make it an implication, we then say this satisfies a gamma P entails Q. We see here we have gamma E entails, and then Q is the conjunction B and C. So we write that as gamma entails E implies B and C. So we've just made the implication, which we wrote in words in red. And the problem now is we see where the real issue of counting is. We do not have enough eggs to go around, but the logic let us write this sentence and treat it as a logical sentence. We need a better logic. So let's find a magical logic that does count. The key idea is to throw out our quick version of not counting the e's. We're going to drop that, and we're simply going to include each e as many times as it appears. So since we needed that gamma comma e entailed c and gamma comma e entailed b, both of them, we now place 2 copies of e on the premises because we're counting the number of times that e occurs. Now, you could ask that I should count the context gamma twice as well, and you could, though it's a convention that gamma isolates all the things in the convention, all the things in the context into one, and so you can reuse the context as many times as you like. In this case, I'm only choosing to count the resource that's scarce, the egg. So things like what is a recipe, what is a cookie, what is a brownie, those I don't need to worry about reusing. Once I've entailed the premise this way, I now see that it's not a single E that entails B and C, it's 2 copies of E. So my implication now counts. The 2 eggs are needed to make brownies and cookies. It's a more precise statement, and it's the kind of thing you need when you're doing resources. Imagine sharing in a large network with lots of computers, and they have to use some files. Sometimes there's only one file, other times you can copy it. Sometimes there's only one timestamp that you can use this data. Sometimes some event is only available to you when the user's there. Because things change in time and space and the resources, counting can be a powerful way to describe what you're trying to do in your logic. If you add counting to your logic, you'll make a stronger version of your story, of your toolbox, I mean. So let's just add that in the simplest way. We don't have to change the symbols. We can keep the arrow for the implication. But now we simply write in somehow how many times we're using the premises. So we'll allow the context to be reused as many times as we like, but the premises that lead to Q, we now number them, something 1 through n. It could even be 0. And then at the bottom, we need to have that many resources available to lead to the implication. This means that the modus ponens gets updated as well. We now know that we need to have exactly that many P's in order to use it to eliminate the implication and get to Q. This is certainly going to take more work to write these details down, but it's exactly what we need if we need to manage information that is scarce. As a shorthand, we have some nice notation that can simplify what we're writing. It is common in mathematical circles to use an exclamation point to mean unique. So if you see an exclamation point something, it says it's the only one of whatever follows. Now to update that, we can put a little n as a superscript. Think of it as a bunch of exclamation marks, n of them. That means that there's a unique one followed by a unique one followed by a unique one n times over. So it's an abbreviation of having n copies of P. It brings it down into a small package. So we would read that as exactly n P's. If we put it together, we can now say the same rules in this small compact notation. If gamma together with n copies of P entails Q, then gamma entails n copies of P implies Q. And if gamma entails n copies of P implying Q, and gamma also entails n copies of P, then gamma entails Q. The premise here has now been matched with the counting. It lets us talk about resources. In summary, here's what we have. Some implications cannot be done independently because they require us to think about resources that are in common amongst the different implications. This can run into trouble with your standard logic. One of the ways to detect this is to think about the content of your sentence. Do they involve shared time or shared resources? Or are these things that can be reused? Maybe if it's a space, you can come back and reuse it later after someone's occupied the space for a period of time. Depending on your situation, you may need to extend your logic to one like this. To keep track of the number of premises is sort of the lowest version of the story, but it gets a little bit more interesting as you expand on some of the logical operators. For a full account of this, you would look at something called linear logic. We'll take it no further than this example, but there's a starting point for some future projects. Until next time.